So next speaker will be Professor Yan Jin from the, I think, let's see, Professor Yan is here. Okay, so I'll introduce her while she's setting up. Professor Jin is currently an associate professor in the School of Computer Science and Technology at the Huazhong University of Science and Technology, Wuhan, China. She received the PhD degree from Computer Science from University of Angers, France in 2016. Her research focuses on the design of effective algorithms for solving combinatorial optimization problems and practical applications, including reinforcement learning, machine learning-based search approaches, hybrid evolutionary algorithms, and heuristic or meta-heuristics. She has published more than 20 papers in the field of meta-heuristics, evolutionary computation, combinatorial optimization, and artificial intelligence. She visited the Queen Mary University of London in 2017 and the Polytechnic Montreal in 2018 as a short-term visiting scholar. She was a Star Trek visiting faculty at Microsoft Research Asia in 2021. And so let's welcome Professor Jin.
Okay, can you hear me and see my screen?
Oh, yeah, it's good.
Okay, thank you. Thank you for the introduction. It is my pleasure to present my recent work in this workshop. The title of my talk is End-to-End Reinforcement Learning for Large-Scale Traveling Salesman Problem. Okay, I will introduce my work from the following four aspects. As we know, the traveling salesman problem is probably the most famous combinatorial optimization problem. The problem is simple to state, but very difficult to solve. Given a set of cities and the distances between each pair of cities, the objective is to find the shortest path that starts from one city, visits all other cities exactly once, and finally returns start city. The problem is not to be NP hard, but sorry. The problem is not to be NP hard and cannot be solved exactly in polynomial time. As one of most studied routing problems, it is challenging to solve instances with tens of thousands of cities in very short time, especially in some time-sensitive real-world applications such as online routing, ride-hailing service. First, I will go through some related works. Many traditional solvers have been developed in field of operations research to solve this problem, including exact algorithm and heuristic algorithms. To best of our knowledge, the best exact solver is called Decoder that applies integer programming with coding plans and branch and bound, but it cannot handle large-scale problems due to memory limits and time limits. Accordingly, heuristic algorithms are often preferred exact algorithms for solving large-scale problems in practice. LKH3 is regarded as the best heuristic algorithms that searches optimal solutions iteratively, which applies a one-tree to estimate edge candidates and uses several neighborhood operations to improve solutions. But it is still time-consuming due to iterative search when it is used in time-sensitive applications. In recent years, a solid number of neural network solvers is proposed in literature using supervised learning and reinforcement learning. Most recent studies apply deep learning approaches to solve TSP. Depending on ways of solution generations, we roughly divide them into two groups, the search-based solvers and the end-to-end solvers. To represent search-based solvers are listed L2I and GCN plus MCTS. The latter solver can solve large TSP instances up to 10,000 cities. It trains a small-scale model by supervised learning and merges sub-heat maps to complete heat map. Then use multicolor tree to search optimal solution with guidance of the heat map. But the search component usually takes a long time to terminate to obtain high-quality solution. And obtained solution performance is very sensitive to selection of search operators. This is highly dependent on domain knowledge. Okay, in contrast, end-to-end solvers that are very efficient in generating solutions and bear much lower dependencies on domain knowledge. Here, we list several end-to-end solvers. The point network is the first end-to-end neural network solver. AM and Pointerformer are attention models by using transformer encoder and autoregressive decoder. To our knowledge, Pointerformer is the best end-to-end solver that can solve the TSP instances with no more than 100 cities. Comparing with supervised learning relying on optimal solutions as learning labels, that is usually unknown when facing the large-scale problem, especially the combinatorial optimization problems. So reinforcement learning has advantage since it can be applied to attain new optimal solutions without requiring existence of ground truth. Moreover, end-to-end deep reinforcement learning algorithms are suitable for some time-sensitive applications, since it has high inference efficiency. However, most of existing end-to-end algorithms only perform well on small instances and can hardly generalize to large scale because of sharply rise in memory consumption and computation time when with the enlarging problem scale. Well, after analyzing the related studies, we confirm our research directions. That is to design a solver that can quickly solve TSP instances with more than 100 cities without relying on any handcrafted heuristic operators. So we designed an end-to-end deep reinforcement learning model to attain high-quality solutions of TSP instances in seconds. The model is called Pointerformer. This is a attention model that consists of transformer encoder and the autoregressive decoder. The encoder takes multiple layers of multi-head self-attention and feed forward on the input instances to obtain embeddings. A multi-point network with single hand attention is important to decode sequentially according query composed of enhanced context embedding. The model is trained with a modified reinforced algorithms. In the following, I will introduce the important components in detail. Here, we propose two novel points for the encoder. First, we propose feature augmentation mechanism to obtain robust embedding. We add a feature to the input, the feature angle to the input, and by flipping and rotating graph, we end up with 24 features for each node. They are input to initial embedding layer. Second, we apply reversible residue networks to scale large instances. This is first applied in solving combinatorial optimization problems. After the initial embedding layer, nodes will go through encoder with 6 residue layers consisting of multiple hand self-attention and feed forward. We made a pair of input and output embedding features to calculate the derivations directly, like this. Okay, for the decoder, we design a multi-point network to autoregressive generate a feasible solution. First, we propose enhanced context embedding as query to interact with all nodes that are to be visited. The enhanced context embedding includes four elements. First, the graph embedding. Second, the partial routing embedding. Third, the first node embedding. Finally, the last node embedding. Different from previous work, the partial routing embedding is additionally used here, since with the same first and last nodes, two nodes may cause different distribution over nodes that are to be visited. Moreover, we design a multi-point network to better use the context embedding. Notice that autoregressive decoder is very fast but memory consuming, mainly due to the attention module used in query at each step. Inspired by multi-head attention, we extended the single-point network to the multi-point network, but different from existing multi-point network in the literature. We use 8 different linear projection on queries and keys. The equation is shown here. We minus Pn by the cost between last node I of partial load and node J to obtain interaction score between R and J. This is to encourage model to start from good policy that is always selecting the nearest node as the next one to visit. Comparing to starting from random policy, this will accelerate training procedure. Finally, we clip the score and mask or visit the node to obtain probability, and finally compute the out probability vector using softmax. Okay, for the training, we choose the reinforced algorithm. The baseline applies device gradient rollout of all instances for policy gradient. But here, we improve the reinforced algorithm. Inspired by previous studies, our decoder also starts from different nodes for each instance with nodes. However, directly applying reinforce will cause algorithm hard to converge because of high variance of costs among different instances. In order to solve this problem, we divided it by the variance so that each sample has seen variance to improve training speed and made the training stable. To evaluate the efficiency of Pointerformer, we compare its performance with soda algorithms. We train and test the Pointer on readily generated instances and verify its generalization of public benchmark. From these two tables, we can see that Pointerformer can scale to TSP instances with up to 500 nodes, while other algorithms, except the ATT, GCN plus MCTS, quickly run out of memory for instances with more than 100 cities. Comparing to search-based approach, our model can obtain the solution maybe that's slightly worse than the ATT, GCN plus MCTS on instances with 500 nodes, but we can see that we can accelerate the computing time by up to 6 times. For example, the 5.9 minutes to 59.35 seconds. In particular, we can attain better results on instances with 200 nodes in less time. Furthermore, our model can well generalize to practical instances with varied distributions without retraining. Okay, this is the performance of the Pointerformer. We have already tried our best to propose several strategies to save memories to the end-to-end deep reinforcement learning. Hope it can solve larger scale, but it can only solve TSP instances with up to 500 nodes. So it is still not satisfied. So it is still not satisfactory in terms of scalability. We want to solve larger TSP with up to tens of thousands of cities in short time. So we further studied this problem, but on a larger scale. Here, we follow the divide and conquer approach and propose a hierarchical architecture. The model is called the H-TSP. How do we to deal the large-scale TSP instances? Our model contains the policy in two levels, which are responsible to solve large scale. H-TSP contain the up level model and the lower model are two levels. The up one is responsible for decomposing the original problem and merging sub-solutions from the lower level. And the lower level model is responsible for the solve the sub problems, but the decomposition will downgrade quality of final solutions. To solve this problem, we let the up level one learn to generate a decomposition strategy. Once a sub-problem is identified, it will be handed over to the lower level one to solve. And then the solution will then be passed to up level one to merge into existing partial route. Here, we propose a grid-based encoder for the up level model. It's an interesting up level model. Okay, by interleaving decomposition and merging, the up level model can learn and the adaptive policy that can make its best decision based on current partial solution and distribution of remaining nodes. We proposed the grid-based encoder to encode the graph as pixels. First, the two-dimensional space is discretized into an evenly spaced 10,000 grids to create a set of pixels. Then, the encoders are divided into different clusters based on the grid they are on. We augment features of each node with vector including absolute coordinate of node, the relative coordinate to the grid center and the node cluster center. If the node has been visited, we also include the coordinates of its neighbors on the partial route. Otherwise, it will be set by 0. Moreover, a variable is used to indicate whether this node has been visited or not. Then, we use linear layer to project them into high-dimensional features and max operations of it to get features of each grid. Sure, there will be some empty grids, so we use the zero patching for them. The combination of each grid forms a procedural image, which is further processed by convolutional neural network, CNN. Now, an embedding vector of instances obtained. The up-level model follows actor-critical architecture to predict a coordinate. Here, the grid-based encoder will output and predict and output a coordinate. Based on this predicted coordinate, the up-level model generalized the subproblems in two aspects. The first, we set subpoints as the node closest to predict coordinate. Then we keep expanding subproblem by selecting neighboring nodes that have not been visited before. Based on k nearest neighbor graph, until the size of neighboring nodes until the size of subproblem reaches the maximum number of nodes and all nodes are selected. Second, we enrich subproblem with a fragment of visited nodes by two directions with equal size of nodes. So the nodes of subproblem are not greater than a predefined number. In this way, we break the existing partial route to obtain a path with two endpoints. We define subproblem as open loop TSP with fixed endpoints. This problem means start from source node, visit all other nodes exactly once, and enter target nodes. We should find a shortest path from this subproblem. Okay, and this will be solved by the lower level model to find an optimal sub-solution. Besides, the up-level model is responsible for the sub-solution merging. To merge the sub-solution into existing partial solution. Next, I will introduce the lower model. This is easy. We just apply an end-to-end neural network that is based on transformer network, which is similar as the previous work, Pointerformer. But here, there is a difference between the subproblem and the TSP. Here, the open loop TSP don't have the same symmetry property due to existing fixed endpoints. We achieve it in an easy way. During node selection, all nodes accepted endpoints will be treated as in TSP without any constraint. Whenever an endpoint is chosen, we let the other one be chosen automatically. The final solution of origin open loop TSP is obtained by removing redundant edge between two endpoints. Okay, here, to improve the performance of up-level and lower-level models, we adopt a joint training strategy. In detail, the kind of lower-level policy will be used to collect trajectories for training up-level model, and the subproblems generated by up-level model will in turn be stored into train the lower-level model. By such an interleaving training procedure, policies in two levels can receive instant feedback from each other. Okay, in the experiments, it is good news that the proposed model can solve the TSP instances with up to 10,000 nodes. Our model achieved comparable results to the SODA algorithms in literature in terms of the solution quality. And we can see that the length of route generated by our model is close to the search-based approach, ATT-GCN plus MCTS, but it requires much shorter time than this algorithm and the other deep learning based algorithms. Moreover, it outperforms our baselines in terms of efficiency. The computation time is 1 or 2 magnitude less than the baseline algorithms. So the high efficiency indicates that our model has potential in many real-world applications that require solving the large-scale TSP in short time, even real time. All right, to conclude, we constantly improve the scalability of TSP solvers through deep reinforcement learning. And we exploit the inference efficiency of end-to-end models, making it usable for time-sensitive practical applications. And the proposed models have potentials to be extended to other large-scale combinatorial optimization problems. In the future, we can try borrowing aspects first, find an effective mechanism to replace self-attention to further improve efficiency of the deep reinforcement learning models. Second, handle the large-scale TSP challenges such as the word TSP. Finally, we can study the models that can tangle various TSP type problems, VRP type problems, and even different combinatory optimization problems. Okay, that's all. Thank you.
All right, thank you very much, Professor Jun, for the interesting talk. So for the interest of time, let's just take one question, and then maybe the other questions can be taken offline. So I see that one audience, Cao Zhiguang, can you unmute yourself and ask a question?
So hello, can you hear me?
Yeah.
Hello, Prof. Jin Yan. This is Zhiguang from Singapore, and thanks for your presentation. It's interesting and informative. I think the results also looks very promising. So I only have one question. So could you please give some advice on how to extend your model to solve capacitated weak routing problem as the CVRP? So in short, I mean, some advice on how to extend your model from TSP or from TSP to CVRP. Yeah, thanks.
Okay, thank you very much. In my opinion, we use we use a hierarchical algorithms for solving the TSP problem by using the divide and conquer idea. In fact, the TSP problem is not very nature problem that can be divided. You can see that we divided the original problem into different sub-problems. That is the TSP with 2 ending points. But the CVRP, this is more nature for dividing. Because there are several recalls, several roads for the VRP problems that starts from the depot to service several customers and return back to the depot. So the CVRP, I think, is more easier to be solved by the divide and conquer. Maybe we can extend our current methods to CVRP problem. It's quite easy. Later I think we can discuss offline.
Yeah, thank you very much, Prof. Jin. Thanks. Yeah.